It's a pleasure to present you today our study in-situ neutron diffraction investigation of relatively manufactured high-manganese steel with various crystallographic texture and cyclic coding. I would like to say at the beginning it's not operando study, but I hope it will be anyway interesting for you. Do I have a reason? Thanks. It is a joint study between two Czech institutes, Institute of Physical Material and Brno University of Technology, Porsche Scherer Institute from Switzerland, and Aachen University from Germany. As you can see from the title, in this study we use high-manganese steel, which is low weight, high alloy steel with excellent combination of strength and activity, which is, for example, important for some energy absorption structures, which can be potentially beneficial for automotive industry. It is good to note as well that manganese is a low-cost alloying element compared to nickel, which is usually used in austenitic steels. And with, in this class of steel, we have quite a large range of manganese content, which has quite large implication on stacking for the energy, and therefore also on undergoing deformation mechanism. We can have a trip effect, but also trip effect. And as you already know, and as you already heard today, both of these deformation processes are highly crystallographic dependent. In general, they are originating from that FCC in the perfect dislocation in FCC metals dissociates on a partial dislocation accompanied with stacking fault energy in between them, and there can be two scenarios when, with respect to loading axis and also the sense of the loading. We can have high Smid factor for leading partial, then for the trailing, and then such kind of orientations are favorable for splitting of partials and therefore for extensive stacking fault energy in the material. The orientation which are denoted by red color are unfavorable for splitting of partials, and therefore the stacking fault energy will not appear that much. And if we realize stacking fault energy on each one-on-one plane, deformation twins will be great, whereas when stacking faults will be on every second one-on-one plane, we will have nucleation of HCP phase, in this case epsilon naught. And actually this is the case for material, what we are looking for. So with this in mind, that we have material which deformation behavior is highly crystallographic dependent, and with that in mind that we have additive manufacturing, which is highly localized method with flexible flexibility to change parameters and also to manipulate structure. We try to pursue the chance to create different microstructures and then subject them to cyclic loading. For that purpose, we adopted the technique or approach which was presented by Professor Matteo Seita and his colleagues, where this actually he will present, I think, on Wednesday. So just very shortly, the main idea is that by bidirectional scanning can enable texture control perpendicular to the direction. So if we will build the samples horizontally, we are able to obtain samples with predominant texture. For that purpose, we had a powder of high-manganese steel from TSM Group raw material company with these characteristics. We had 21% of manganese. And as I said, we did horizontal printing. At first, we printed blocks. Afterwards, we machined the cylindrical samples. We used bidirectional scanning without rotation. And the printing pattern was in our atmosphere. The plate was preheated to 100 centigrade. We obtained quite low porosity, which is critical for fatigue loading. The macrostructure looked like this. You can nicely see that we had quite extensive epitaxial growth from layer to layer, which is also visible from SEM images over there. Fatigue tests were done on severe hydraulic machine, fully reverse cycling at the constant strain amplitude 0.8%, and this strain rate. With promising result what we get there, we submitted proposal for in-situ neutron diffraction or fatigue testing in Oak Ridge, and we actually emulated the test here with some fine measurement at 30 cycles, where the strain was decreased to this value. And we collected data into the two detector banks and used it later on for analysis. Here is already the characterization of as-built structures. You can see that we were able to produce 4 structures which are different to each other. We have one microstructure which should be feasible for phase transformation in compression, and then we have 2 microstructures, so let's say so-called O11, where we have quite large spread of the orientation, but anyway it's close to O11 or 133. Then 111 sample with predominant 111 grains. And then we had also a random sample, so-called random sample, where we used a conventional scanning strategy with 66 degree rotation between each layer. Here is already fatigue results, mechanical data. You can see here the cyclic behavior of all 4 microstructural variants. And one common thing is that for all of them, we have cyclic hardening during the whole fatigue life. But still, there are some notable differences between the material, between the variants. For example, for 001, we have the least pronounced cyclic hardening, which is just very mild and steady. 111 has the highest cyclic strength all along the fatigue life, and 011 experienced the most pronounced hardening in this section, which is between approximately 10 to 80 cycles. We presented the results in cumulative plastic deformation because since we have textured materials, the elastic Young moduli of the samples are very different, and therefore to represent the results in number of cycles is not very representative. So for that reason we use cumulative plastic deformation. Also, it is interesting to have a look on initial value of stress amplitudes, which kind of follow single crystal behavior for FCC methods, where 001 has the lowest strength, followed by 011, then random, and then 111 material variant. Here is, so actually, with this in mind, it's visible that we have significant cyclic hardening, which we assume that is coming from phase transformation, and which is supported by neutron data and neutron data analysis. Here is FCC reflection intensity change for selected grain families. Advantage of cyclic loading is that we don't have lattice rotation, so actually we can compare the initial value of the intensities of given planes with the evolution, and we can attribute the change directly to the phase transformation. And as we already said during the motivation, we assume that they should follow crystallographic dependency. For that purpose, I put here the IPF, where you can see the difference of Smid factor between leading and trailing, where the negative values are for the feasible transformation intention, and the positive values are for feasible transformation in compression. And as you can see, we have two grain families, namely 024 and 113, where the intensity doesn't change, nearly doesn't change during the whole fatigue life. And for these planes, we have the difference roughly around 0, which are these two directions, which follow nicely. Then we have 011, which is feasible for deformation and compression, and it nicely follows the magnitude of this Smid factor difference, where for 111 we have slightly larger change in intensities with following 011, and the most feasible is 133 orientation, as you can see. So this nicely agree with what we expected, and from that we were able also to plot Martin's diffraction evolution. Since we don't have strictly in some variants we don't have so strong texture, there is a kind of combination of and some scatter, some disorientation scatter. We don't have so clear behavioral idea, but still it's visible that 011 has slightly faster kinetics of the transformation compared to 111, but at the end they reached quite similar values of the Martin-Knight diffraction. Whereas the random was the third one, and 001 sample reached the least of the Martin-Knight. The next thing what we had to look as well was the load sharing between the phases. And here is the situation in sample 011 in first cycle during the ramp up. So this is the very beginning of the measurement where we don't have ACP phase in the material, and you can see that 111 plane exhibits plastic behavior, and actually the slope nicely follow the expected behavior for FCC metals. And 220 plane, you can see that undergo plastic deformation over here, whereas 200, 311 behave elastically, and there was a load transform from 220 plane. With further cycling, the situation changed rapidly. This is from cycle number 300, and you can see here already full loop with tensile part and compression part. And the prominent change is that here we had plastic deformation for 2 plane, but over here we can see fully elastic behavior as well for plane 311, and still the same situation is for 111. We assume that during the loading at initial stages of fatigue life, the austenitic phase strengthened, and therefore the yield strength increased for these grain families. and therefore we don't see any plastic deformation, for example, in case 220, and there is a load transfer to 200 with some plasticity as well. In the case of ACP, it's interesting that actually it's visible that ACP phase, the epsilon martensite, takes the load, or actually plastic deformation, which is visible for these two reflections, for these two planes. And for plane 1 or minus 1, 2, we see elastic behavior. So again, it's a load transfer from these two grain families to 1 or minus 1, 2. Let's have a look at the end also the post-mortem EDSD, how look the structure. This is the macro view, and you can already see that, which also already obvious from neutron data, we have quite significant amount of epsilon, and here is visible the distribution. And in the detail map, you can see numerous martensitic LEDs in the structure, which we believe presents additional obstacles for mobile dislocation. So we have a kind of dynamic hole patch effect in this material as an additional strengthening mechanism. Let me conclude my talk. So we were able to produce 4 distinctly different microstructures, which we subjected to cyclic loading, and with low porosity, which is important for fatigue. We had distinct differences in cyclic behavior, in cyclic hardening of the materials, which can be explained by crystallographic condition with different affinity to phase transformation. The kinetics of the phase transformation agrees well with the crystallographic dependency of Smid law for partial dislocation, and therefore the epsilon martensite volume fraction strongly vary between the microstructural variants. Of course, here in this case, it was not so dominant, and we saw that at the beginning of the fatigue test, we had typical plastic behavior for austenite, whereas in later stages of fatigue life, the nucleated epsilon martensite accommodate majority of the cyclic plasticity, whereas austenite strengthened and is predominantly loaded in elastic regime. And we can conclude that 111 texture microstructure had the best fatigue performance, whereas we had high cyclic strength due to crystallographic inherited high yield strength, and also still quite good phase transformation. Thank you for your attention.